We've always asked, where do we come from and where are we going? In 2025, cosmologists are still divided, but new surveys have sharpened the debate. The Dark Energy Spectroscopic Instrument released data on nearly 15 million galaxies, hinting that dark energy may not stay constant if it changes with time. One extreme scenario is the so-called Big Rip, where even atoms are pulled apart. This possibility doesn't prove anything yet. It only raises deeper questions about how the universe ends. To even approach an answer, we first need to understand just how small our place really is. The scale of nothingness. When astronomers speak of the scale of nothingness, they mean something precise. The recognition that most of space, when measured against human standards, is almost entirely empty and staggeringly vast. Earth may feel immense to us, with continents, oceans, and landscapes so large they defy our daily sense of distance. Yet the moment we compare it against cosmic structures, its size collapses toward insignificance. Numbers that appear straightforward on paper quickly overwhelm the imagination. The solar system provides the first glimpse of this scale. Light itself, moving at nearly 300,000 kilometers per second, takes just over 8 minutes to reach Earth from the Sun. By contrast, for light to reach Neptune, the outermost major planet, the journey lasts more than 4 hours. Such distances sound incomprehensible, but what they highlight is that even billions of kilometers, the width of our planetary system, barely registers when placed against the galaxy that holds it. The Milky Way stretches around 100,000 light-years from one edge to the other. To picture this, imagine trying to locate the solar system inside such a structure. The orbit of Neptune, which feels enormous to us, occupies less than a pinpoint. At this scale, our entire system is a dot, requiring thousands of zoom levels to distinguish within a spiral disk of some 400 billion stars. And the Milky Way is not an outlier. In fact, it is a fairly ordinary spiral galaxy, modest when compared with some of its larger neighbors. Extending outward again, astronomers have cataloged millions of galaxies with modern instruments. Projects like the Euclid mission and James Webb have revealed vast populations farther than we can easily describe, while the Vera C. Rubin Observatory in Chile is expected over the next decade to chart on the order of 20 billion galaxies. Each one consists of stars numbering in the billions. The statistics begin to suggest a universe structured more like a swarm than a map, clusters upon clusters tied together by filaments, with dark voids stretched between them. One of astronomy's most memorable illustrations is the comparison between stars and grains of sand. Specialists often note that if you could gather all the sand found on every beach across Earth, the total number of grains would still be fewer than the stars scattered through the observable universe. The point is not exact precision, but a way to frame the immensity. Every coastline, every desert still falls short of representing how many suns are out there. And because many of those stars host planets, the number of worlds exceeds anything our imaginations can fully tally. This way of counting forces us to rethink scale in human terms. For someone hiking up a mountain, the horizon gives the sense of immense distance. For an astronaut, however, the Earth itself shrinks into a small blue sphere. For astronomers, even our solar system disappears once they pan out far enough, leaving only a cluster of coordinates inside an indistinct spiral. With each step of magnification, our home reduces to a smaller fraction of the whole until the numbers defy casual comprehension. Part of the challenge comes from how our minds evolved. Human perception operates on lengths of meters, kilometers, hours, convenient measures for daily life. But cosmic measures skip in leaps of light years, millions or billions at a time. When told that the nearest star is over 4 light years away, more than 1,200 times farther than Voyager 1 has traveled in half a century, we can compute the statement yet struggle to feel its meaning. The gap between calculation and intuition is what makes the notion of nothingness so difficult to absorb. Still, the purpose of reflecting on scale is not to erase Earth's significance. In many ways, the opposite is true. Astronomers emphasize these statistics to show how remarkable it is that such a minuscule dot harbors life at all. If stars outnumber grains of sand, then Earth represents one of those rare spots where the grains themselves can ask about their place within the beach. Tiny, yes, but uniquely aware. This recognition changes how we classify words like large, important, or ordinary. The Sun is cataloged as a typical star, falling neatly within the spectrum of common stellar mass and brightness. Yet to us, it is not typical at all. It is a light, and heat upon which everything depends. ordinary to the galaxy, but indispensable here. The same applies to Earth, technically smaller than specks of dust when scaled against the universe, but the central stage for everything we know. So the scale of nothingness leaves Earth barely measurable. It also leaves us with a profound paradox, vanishing in a statistical sense, yet vastly meaningful in a personal one. That tension, the gulf between our numerical insignificance and our experiential importance, is what fuels both scientific measurement and philosophical wonder. And as immense as the visible universe appears, what we can observe may represent only a fraction of its total content. Surveys catalog galaxies and map their light, but they also reveal something stranger. Most of the universe does not shine at all. This realization sets up a deeper puzzle than size alone, because beyond the stars and galaxies, there exists a hidden majority we cannot see directly. The universe's invisible majority. If most of what exists in the universe cannot be seen directly, how can we be confident it is there? The answer lies in patterns that betray the influence of something hidden. Galaxies rotate too quickly for the visible mass of their stars and gas to provide enough gravity to hold them together. If only the matter we see were present, the galaxies should have torn themselves apart long ago. They have not, which suggests an unseen glue, dark matter. On grander scales, the way the expansion of the universe speeds up instead of slowing down implies yet another unseen component, this time a force pushing outward. That unknown influence is called dark energy. Together, these two invisible ingredients appear to account for about 95% of the mass energy in the cosmos, leaving less than 5% for stars, planets, gas, and everything we are familiar with. They remain hidden because they do not shine. Dark matter and dark energy give off no light, and they interact only very faintly with particles we can detect. Their presence is inferred instead. Astronomers trace galaxy rotation curves, map how clusters bend light in a process called gravitational lensing, and analyze the faint ripples in the cosmic microwave background. Large-scale sky surveys track how galaxies cluster over billions of years, and Type Ia supernovae allow distances to be measured precisely. These independent methods consistently point to the same puzzle. Most of reality is invisible to the eye, yet it shapes almost everything we can measure. The puzzle is so important that experiments on Earth have been built to search for dark matter directly, even if its properties remain obscure. Physicists design underground laboratories deep beneath mountains, far from cosmic rays, to shield delicate detectors. The expectation is simple. If dark matter is made of particles streaming through space, one of them might, on rare occasion, collide with an atom in a detector. To maximize chances of noticing, instruments are constructed at extreme sensitivity. Some use liquefied noble gases like xenon, sitting silently in vast tanks, waiting for the flash of light that signals a collision. Others lower temperatures almost to absolute zero, where quantum sensors can pick out the faintest shiver produced by an interaction. These are examples of how the search works in practice. Underground ultra-cold, and straining to detect the rarest events imaginable. But physics demands rigor. Small signals have often been mistaken for massive discoveries. Past claims of possible detections have later been reinterpreted as background noise, radioactive impurities, or miscalibrations. Announcements that at first appeared to reveal breakthroughs turned out to be red herrings. The effort has been historically defined by false alarms and necessary retractions. Each disappointment emphasizes how high the bar of proof must be. No single flicker on a screen is enough. Only consistent, reproducible results across multiple instruments can establish something new. In 2025, the sheer volume of data being collected from detectors is too large for human teams to sift alone. Artificial intelligence now processes much of it, searching for correlations and anomalies in continuous data streams. Machine learning does not magically solve the mystery, but assists by filtering through the noise faster and more thoroughly than manual checks. Algorithms can flag unusual features that might otherwise be overlooked, though such alerts are only the beginning. So far, none of the flagged anomalies have survived the strict follow-up required to be called a discovery of dark matter. These digital tools extend human efforts, but caution remains essential. Machines can only find signatures they are trained to see, and their outputs must be tested as rigorously as any human analysis. Speculation about what might constitute dark matter continues, and not everyone insists that it must be some exotic particle. Alternatives argue that perhaps our understanding of gravity itself needs modification at very large scales. Such frameworks aim to explain galactic stability and cosmic structure without invoking invisible substances. While they hold less support compared to particle models, the absence of direct detections has kept these possibilities alive. Each passing experiment that fails to find a particle both sharpens the search and leaves the door slightly open to the idea of new physical laws. Alongside this, one of the most pressing questions in cosmology focuses on dark energy. Unlike matter, which clumps into galaxies and stars, dark energy seems evenly spread across space, exerting a smooth, repulsive effect that accelerates the universe's expansion. The mystery extends beyond its invisibility. Even theoretical attempts to explain its nature come up short. Quantum mechanics predicts vacuum energy, but at levels so staggeringly higher than measured reality that the numbers seem impossible to reconcile. Many physicists admit frankly that they do not know what dark energy is. Some suggest it could change with time, a possibility with profound implications. Here lies one of the biggest scientific developments of 2025. Projects like the Dark Energy Spectroscopic Instrument, which collects millions of galaxy spectra, and large compilations of supernova data such as Union 3 are supplying the strongest hint so far that dark energy might not be perfectly constant. The evidence remains tentative, but were it to hold, it would suggest the strength of this invisible force evolves with cosmic history. Such a result would challenge the standard model of cosmology and alter predictions of the universe's fate, whether it accelerates into emptiness indefinitely, slows to a halt, or even reverses. Despite the uncertainty, scientists take confidence in precedent. Hidden phenomena have often been discovered indirectly before instruments ever captured them directly. The planet Neptune was predicted based on gravitational effects it exerted on Uranus' orbit, long before anyone saw it in a telescope. Electrons were inferred from the behavior of electric currents decades before they were imaged as particles. Dark matter and dark energy may be following in that tradition, first glimpsed through their fingerprints, later perhaps revealed more explicitly. This indirect approach keeps curiosity alive even without direct sightings. An algorithm's anomaly that disappears in follow-up is not a failure, but a step in refining the path. Each partial result, negative or positive, narrows the range of possibilities and informs the next generation of detectors, telescopes, and theories. The process does not provide dramatic final answers overnight, yet it steadily pushes the frontier forward. It is also ironic in a way that what we cannot see exerts more influence than what we can. The stars, galaxies, nebulae, and planets we admire make up a fraction of cosmic reality, while the unseen portion controls the story. Without dark matter, galaxies would fly apart. Without dark energy, the expansion of the universe would behave completely differently. Hidden components, though mysterious, define the visible universe we encounter. And as ongoing projects gather new data sets with increasing resolution, scientists are left in a position of suspense. They do not yet have the answers, but they are now closer to real tests than ever before. The invisible majority still evades capture, but the effort to study it has redefined cosmology entirely, which raises another question. If so much of the universe is hidden, what can modern telescopes actually show us? The answer turns our attention to light, not the unseen components, but the earliest visible galaxies themselves, captured when the cosmos was still in its infancy. James Webb, the baby photo machine. The clearest tool for exploring these early cosmic mysteries is the James Webb Space Telescope, sometimes nicknamed the baby photo machine for its ability to capture the universe in its youth. With its enormous mirror and unmatched sensitivity to infrared light, it allows astronomers to look back billions of years, well into the first few 100 million years after the Big Bang, when the very first galaxies were forming. In 2025, Webb continues to send down results that are rewriting expectations, showing not only individual distant galaxies, but an entire population of them, far more numerous and mature-looking than models anticipated. Surveys like Cosmos are now cataloging nearly 1 million galaxies across cosmic time and finding roughly an order of magnitude more at extreme distances than pre-launch simulations predicted. That matters because theory long suggested the early universe should have been slow to organize. Instead, Webb's data shows some of these faraway galaxies as surprisingly massive, bright, and enriched with heavy elements. In practical terms, telescopes have spotted systems that existed when the universe was still less than 1 billion years old, shining as if they had skipped ahead on the timetable. For scientists who spent decades refining cosmological models, this raises a sharp question. How could such heavy, metal-rich galaxies form so quickly? Three leading possibilities have emerged to explain this mismatch. One idea is that the distribution of dark matter in the early universe may have included unusually dense clumps. Those clumps could have created wells of gravity strong enough to pull gas in earlier and faster, producing galaxies far ahead of the expected schedule. Another candidate explanation is that star formation itself unfolded more explosively than models assumed, with successive generations of stars being born, burning through fuel, and dying in mere tens of millions of years, seeding heavier elements into their host galaxies almost immediately. Third option is that part of what we are seeing lies in how surveys interpret faint objects at extreme redshifts, meaning some readings could be biased, and ongoing reevaluations might refine which objects are truly as massive as they appear. Even with those uncertainties, the picture Webb is painting has continuity across independent teams and approaches. Researchers measuring spectra at different wavelengths, using different analysis techniques, are all converging on the same finding: the young cosmos was more complex and varied than expected. Some early galaxies do still look small and faint, lining up with the anticipated picture, but others are dramatically oversized for their age. This diversity suggests that evolution did not proceed evenly across the universe. Some regions may have raced ahead precisely because they sat at intersections of the cosmic web where matter was particularly dense. Webb's value lies not only in imaging these ancient systems, but in measuring their physical details. Its detectors catch redshifted light, radiation stretched as the universe expands, which can then be precisely measured to determine distance and age. In many cases, spectral analysis reveals the fingerprints of heavier elements, what astronomers collectively call metals. Since metals are forged inside stars and spread when those stars explode, their early and abundant presence in galaxies only a few 100 million years after the Big Bang means star formation was already vigorous. That alone alters how scientists think about the first phases of reionization, the cosmic transition from an opaque fog to transparent space. The nickname baby photo machine comes from this power. Just as a snapshot captures a baby at an age before memory existed, Webb is providing images of the universe when it was still in its earliest stages, too young to resemble the structures we take for granted, yet undeniably already forming them. Instead of blurry, indistinct smudges, Webb produces defined structures, showing that galaxies could assemble into organized systems shockingly early. In effect, we are no longer speculating about the first galaxies, we are watching them unfold in detail. What unsettles cosmologists most is not Webb's technical prowess, but what its data imply. If massive galaxies existed so soon, then the timeline for making heavier chemical elements might need to shift earlier. Chemically enriched environments could have appeared long before previously believed. That raises speculative, but still unproven questions. If metals are already widespread at early times, then the raw ingredients needed for rocky planet formation might also have appeared earlier. But it is important to underline that this is only a possibility. No current JWST data confirms that planets or life emerged early. All we can responsibly say is that if enrichment came fast, then conditions for the building blocks may have been available sooner. That if remains large and unresolved. What is not in doubt is that Webb has deepened the tension between theory and observation. Models that once described a predictable progression toward complexity must now account for the reality of early giants. It echoes earlier moments in science when new tools disrupted consensus, Galileo's first glimpses of moons orbiting Jupiter against expectations, or Edwin Hubble's discovery of the expanding universe that overturned static cosmology. In this same tradition, the Webb telescope is exposing the shortcomings in models that had seemed reliable just a few years ago. Astronomers described the feeling in 2025 as equal parts exhilaration and frustration. Finding galaxies 10 times more numerous at early epochs than anticipated is thrilling, but it also generates more questions than answers. Each new image carries with it a new puzzle. Why this galaxy in particular? How dense was its environment? Which processes could assemble such mass in so little time? And if Webb has already found them, are there still more extreme examples? Sitting just beyond its reach? The telescope's reach is not confined to the deep past. While its flagship results spotlight the youngest galaxies, Webb also returns detailed images of local phenomena, from auroras on Jupiter to star-forming regions in the Milky Way. These serve as checks and balances, letting researchers understand physics close at hand while applying the same rules to the far universe. This dual role, studying both the nearby and the ancient, builds confidence that the strange results at high redshift are not illusions, but genuine features of cosmic history. What makes these discoveries particularly powerful is that they are not isolated. Instead, they fit into a growing catalog of consistent anomalies. Multiple spectra, across multiple sources, all indicate early activity richer than predictions. By 2025, this is not a one-off curiosity, it is a trend. That is why the baby photos matter. They turn speculation into consistent observation, demanding that theory keep pace. Science often advances this way. Surprising data surfaces, consensus falters, and eventually models adapt. Webb's catalog of unexpectedly mature galaxies is now pressuring cosmologists to rethink their assumptions about how structure formed in the early universe. Whether the solution lies in revised models of dark matter, new physics in star formation, or simply deeper refinement of observations, the process is underway. Standing back, the lesson is straightforward. The young universe was not as simple or as slow-moving as earlier models suggested. It was brighter, busier, and more uneven, with regions racing ahead while others lagged behind. That fundamental shift in our picture is Webb's greatest contribution so far, showing a cosmos that was always more dynamic than we expected. And this reimagining of the restless young universe naturally pushes us toward the next frontier. Because while Webb reveals the skies as they once were, other clues about the past have literally fallen at our feet. Ancient fragments that carry stories from long before planets like Earth ever formed. The meteorites that outsmarted Earth. When scientists talk about records left behind by the early universe, some of the most durable are not in data archives or telescope images, but in the solid form of meteorites. They are fragments of matter older than Earth itself, more than 4 billion years old, and they preserve chemical details that the young planet erased long ago. Each stone that survives a fall to Earth acts as a natural archive, storing the chemistry of the early solar system and, in some cases, the chemistry of stars that lived and died before the sun was even born. Recent fieldwork in 2025 has kept adding to this long-running archive. Teams traversing the empty white expanses of Antarctica have recovered specimens with atomic fingerprints that differ from anything found in ordinary terrestrial material. Antarctica makes an unusually good search ground. Dark meteorites are easy to spot against bright snow, and the frozen conditions preserve their interiors from contamination. For these reasons, many of the most pristine samples ever studied come from Antarctic ice fields. Some of the recent finds contain rare isotopes, arrangements of protons and neutrons that point to origins in stellar environments predating the solar system. This alone tells scientists they are handling material not shaped on Earth, but inherited from an earlier generation of stars. Fragments of iron meteorites can also display crystalline signatures unfamiliar to normal geology. One notable feature is the Wittgenstein pattern, intersecting metallic lines that only form if molten metal cools at an exceptionally slow pace over millions of years inside large parent bodies like asteroids. The Earth's environment never allows such textures to form naturally, since surface metals solidify far more quickly here. Each cross-hatch pattern is therefore a direct record of cosmic time, a marker of processes that occurred on scales much longer than human history before being frozen into a lump of iron and eventually tossed across space to reach our atmosphere. What gives these samples even more significance is their mixed heritage. Some of their isotopic contents trace back to cataclysmic stellar events, particularly supernovae. Those stellar explosions create heavy elements, iron, calcium, nitrogen, oxygen, that later become the stuff of planets and life. In meteorites examined in recent years, scientists have identified inclusions showing clear signals of pre-solar grains. These microscopic crumbs formed in ancient stars before our solar system assembled. To hold them is, in a literal sense, to hold pieces of other suns. Meteorites thus remind us that Earth is not an isolated creation, but the product of earlier stellar generations, with their ashes falling back into new planetary systems. Aside from their physics, these meteorites offer a bridge to more human ways of thinking. Some researchers describe them as cosmic family elders, pieces of matter far older than Earth that still arrive unannounced, carrying memories of the universe's earlier generations. It is a useful metaphor because it captures how meteorites extend our family tree of matter far beyond local history. They are awkward guests but carry knowledge no one else has. Naturally, the question arises, what specific information do these fragments carry that matters for life itself? Here the conversation becomes especially interesting. Laboratory studies of certain meteorites have revealed carbon-rich molecules, organic compounds much more complex than simple arrangements of hydrogen and carbon, but still far short of life. These compounds look like plausible precursors, molecules capable of linking up under the right conditions and forming the chain central to amino acids or nucleic acids. They represent chemistry leaning in the same direction as biology. This finding matters because it broadens how we think about life's origin. If meteorites routinely contain such molecules, it suggests that chemistry that eventually produced life on Earth was not unique to our planet, but common in interstellar space. Space itself is capable of manufacturing part of biology's toolkit. Life still required a special setting of liquid water, energy, and stability on Earth, but the raw ingredients could have arrived long before, delivered by falling stones. Scientists speak cautiously, but these organics are plausible contributors to early Earth's feedstock, supporting the idea of panspermia, or seeding as one viable pathway among several for life's beginnings. Confirming such claims requires careful laboratory methods. Researchers take measures to separate meteoritic interiors from the surfaces that touch air, soil, or ice. Chemical and isotopic analyses then sort what is truly extraterrestrial from what could have seeped in after impact. When unusual isotopic ratios appear, those that do not match any known terrestrial pattern, they give confidence that the molecules really came from space. The new finds of 2025 have provided exactly this sort of evidence, indicating unmistakable extraterrestrial organics preserved inside rocks since before Earth itself existed. One can imagine this process in very practical terms. Early Earth, still hot and unstable, was bombarded by countless comets and asteroids. Many of those carried the same types of compounds we detect now. Each impact would have scattered materials, some of which dissolved into pools of water, where energy from sunlight, lightning, or geothermal heat could drive further reactions. In this picture, meteorites acted like couriers, dropping off packets of chemistry that the young planet could then store, rearrange, and build upon. They did not guarantee life, but they widened the field of possibility dramatically. The broader implication is equally striking. If space routinely manufactures and delivers these molecules, then other young planetary systems elsewhere likely experience the same deliveries. The recipes for prebiotic chemistry may be dispersed across the galaxy rather than restricted to our neighborhood. This makes the probability of life elsewhere higher, not certain, but less dependent on Earth having been an exception. The meteorites therefore tie nicely into the wider search for habitability on exoplanets, giving researchers reason to expect that complex chemistry should exist wherever stony bodies orbit new stars. Practical challenges remain in studying them. How do scientists know the molecules inside a blackened rock in a desert are not just residues from soil or rain? The answer lies mainly in preservation environments. Antarctic meteorites become encased in ice and often remain untouched for thousands of years before researchers collect them. Desert meteorites, when carefully excavated, can be cleaned and sliced to access untouched interiors. These strategies ensure the organics measured today represent space chemistry rather than Earth contamination. The paradox here is that some of the harshest, most lifeless landscapes on Earth, the dry expanses of deserts and the frozen plains of Antarctica, are exactly where we find the best evidence for how life's chemistry might have begun. A frozen horizon may look empty, but scattered across its surface are fragments that carry history written in isotopes and carbon chains. These records are not vague suggestions, but tangible artifacts, evidence that our planet's molecules were shaped by wider forces operating long before there was a planet to stand on. This is why meteorites are said to outsmart Earth. They contain structures and chemical stories our planet erased during its violent youth. They preserve compounds our environment could not make or could not protect for billions of years. They reach across cosmic history to deliver not certainty but strong clues that the building block of life existed long before the ground beneath our feet was solid. In our hands, they are the most direct proof that cosmic matter carries memory. And just as they push us to rethink origins, other mysteries of the universe push even harder, raising questions not about beginnings but endings, and whether reality itself is capable of remembering anything at all. The black hole paradox. Physicists face another frontier that tests the limits of what we call reality itself, the black hole information paradox. For nearly 50 years, this puzzle has stood as a direct clash between the two most reliable frameworks in science. General relativity, which describes how gravity bends space and time, suggests that when matter falls through a black hole's event horizon, the information about it disappears forever. Quantum mechanics, by contrast, insists that information about any physical system must always be conserved. The paradox arises because both frameworks cannot be correct in this case, and yet both have proven astonishingly successful everywhere else. Stephen Hawking's original calculations made the conflict unavoidable. He showed that black holes are not completely black, but slowly emit radiation known as Hawking radiation. The problem is that this radiation is thermal, meaning it looks random and carries no imprint of the matter that fell in. Taken at face value, this implies information is lost, wiped from existence. That conclusion broke with quantum mechanics' strict conservation rule and created a split in physics: either accept that black holes shred records forever, or concede that something deeper must be going on. For decades, the debate remained frozen at this impasse, with neither side yielding. Instead of being a question confined to whiteboards, researchers now attempt to model pieces of the paradox using quantum processors. These are not full simulations of an astrophysical black hole, but carefully designed toy models, simplified frameworks that capture specific aspects of quantum gravity. Quantum computers happen to be well suited to this task. Because they naturally exploit superposition and entanglement, the same features believed to govern matter near an event horizon. For the first time, scientists are watching how entangled particles behave when one partner falls into a simulated black hole while the other remains outside. So far, the results are suggestive rather than decisive. Early simulations point to a possibility long theorized. Information may not be destroyed, but scrambled into correlations hidden within the Hawking radiation, so fine and dispersed that no realistic observer could ever decode them. In principle, at least, the data is not erased. It exists in a form so scrambled that it is effectively lost to practice. This reframes the debate. The core question is no longer just destroy or preserve, but whether preservation that is impossible to access should still count as a solution to the paradox. A useful analogy is burning a book. To the human eye, the book is gone, reduced to ash, heat, and smoke. Yet physics holds that the microscopic details of the flame, the molecules dispersed in the air, and the vibrations imparted to the environment contain the full record of what was burned. The information is conserved, but so hopelessly scattered that reconstruction is practically impossible. Toy model black holes generated on quantum computers might behave in similar fashion. They would act less as obliterators and more like machines encoding data into nearly unreachable complexity. This line of reasoning offers a partial way out of Hawking's original conclusion. If, theoretically, the fine structure of Hawking radiation encodes the information, then physics retains consistency. No part of reality then permits true erasure. But for a real observer, the effect is the same as destruction. Even with unlimited patience, the correlations are so faint they cannot be reassembled. In practice, we are confronted with a kind of effective loss. That slippery distinction, conserved in principle, unrecoverable in practice, is at the heart of current research. Quantum entanglement complicates matters further. Some simulations indicate that particles crossing the horizon may preserve subtle correlations with partners left outside, suggesting the horizon is not a sharp cut but a permeable filter. Instead of information plunging past a one-way barrier, it might be smeared across the boundary through entanglement. That challenges the simple image of a black hole as a sealed void and instead portrays it as part of a wider web, interconnected with the universe beyond. Skepticism remains necessary. These are not astrophysical black holes, but mathematical constructs running on current quantum processors. Modern devices can only manage systems of modest size, nothing close to the billions of particles involved in reality. The simulations capture patterns and principles, not the full complexity of collapsing stars. At best, they provide hints, clues about how information might be managed by nature, not proofs of what nature actually does on cosmic scales. For that reason, physicists emphasize caution. Intriguing signals in laboratory models may not survive translation into full theory. Even so, the progress matters. For decades, the paradox lingered as a theoretical wound, unsolvable because of the incompatibility of general relativity and quantum mechanics. By bringing actual computations into the mix, the debate takes on a more experimental character. New generations of quantum processors become laboratories for questions once thought untestable. By itself, that shift represents a step forward. The paradox is no longer just an argument about logic, but a question accessible to empirical methods. If these approaches prove sound, they may restore a reassuring principle that the laws of physics do not permit complete erasure. If black holes preserve everything, then in principle the universe contains a permanent record of all events, no matter how well hidden. That deepens the mystery of causality, because information released after eons would still be part of the chain of cause and effect. Our usual sense of time, as a straightforward arrow from past to future, grows cloudy under such a framework. One way to illustrate this is to ask, if information is preserved but emerges billions of years later in scrambled radiation, what does that imply for sequences of cause and effect? The idea raises uncomfortable possibilities. Could the future contain echoes strong enough to force revisions of the past? Not in practice, but conceptually, the neat division we rely on. The past is fixed, the future is open, becomes less clean. The question reaches toward free will, determinism, and the role of information in defining what events can unfold. Yet it is important not to leap into sharp conclusions. The toy model results are only the first probes into a question many expected to remain impenetrable. Even as we consider their implications for time and causality, the field remains careful not to declare the paradox solved. More accurate simulations, stronger theories, and deeper experiments will be needed before black holes can be said to have revealed their secrets. The paradox endures as part of a wider struggle, reconciling our best descriptions of gravity with our best descriptions of the quantum. For now, black holes continue to act like signposts marking the place where these two theories break down. They highlight the limits of our knowledge, and in doing so keep science anchored to its most fundamental mystery: what rules truly govern the universe at its extremes. As the research advances, the narrative of 2025 is defined by cautious opportunity. Quantum processors provide a new toolkit. Early evidence points toward deep encoding rather than outright destruction, and the conversation has shifted from philosophy to something closer to experiment. No decisive solution exists yet, but a path has opened. The implications for physics are enormous, but so too are the implications for how we think about time, memory, and determinism. And once questions of information, history, and causality emerge, another possibility presses in from theory. Some researchers argue that the equations themselves point toward realities even stranger than hidden records within black holes. There may be more than one universe altogether, and signs of those possibilities may already be hiding in the data we collect today. Parallel universes, or just a math trick? Is it possible that what we call our universe is only one among countless others? Physicists frame this question not just as science fiction, but as a serious, if speculative line of inquiry. The notion of a multiverse has evolved from playful thought experiments into hypotheses shaped by formal mathematics and data analysis. Yet in 2025, it remains perched on the narrow edge between imaginative possibility and testable science, with new ideas sparking both excitement and skepticism. One of the primary places where hints might show up is in the cosmic microwave background, the faint radiation left over from the Big Bang. This afterglow is almost uniform, but not perfectly. It has tiny fluctuations in temperature that serve as fossils of the early universe. Decades of observations by satellites like WMAP and Planck showed those fluctuations are broadly consistent with cosmic inflation, the rapid expansion that occurred in the universe's first fraction of a second. Still, small anomalies have attracted interest, such as alignments or cold spots that don't fit smoothly into standard models. Some researchers have suggested that such irregularities could be scars from bubble collisions, evidence that other universes once brushed against ours. But that suggestion is tenuous. Analyses of Planck and WMAP data have searched carefully for bubble collision patterns. So far, the results have shown no statistically significant signal. What has been found are anomalies within the range expected by chance when measuring so many data points. This doesn't mean alternatives are ruled out. It simply means there's no convincing evidence yet. Advocates highlight that a replicated structure, a clear hot or cold spot consistent with predictions of a bubble imprint, could change the conversation. To this point, however, nothing in the available datasets clears that bar. Observational hints remain tentative at best, and many experts caution against mistaking noise for discovery. Parallel to inflationary bubbles is the contribution from quantum theory. The many-worlds interpretation developed in the mid-20th century suggests that every quantum event produces multiple outcomes, each realized in its own branch of reality. In this view, even the simplest event, an atom decaying or a coin landing heads instead of tails, creates a separate universe where the alternative outcome holds true. For decades, this interpretation lived mainly in philosophy and theory, but the development of quantum processors has given it renewed visibility. Take Google's Willow processor. It has achieved precision in tracking quantum states beyond what earlier machines could manage. Its architecture allows multiple qubits to remain stable and correlated while performing computations no classical system can attempt. Some commentators, echoing ideas first proposed by physicist David Deutsch, argue that such quantum computations feel like they could be tapping into parallel realities. But most physicists do not treat this as evidence. The mainstream view is measured. Quantum processors demonstrate quantum mechanics in action, yet no result has proven the existence of parallel worlds. Suggesting otherwise risks stretching beyond what the data support. That distinction matters. The fact that a quantum computer can perform calculations at speeds unimaginable for classical machines is extraordinary, but it does not require additional universes to explain it. Quantum superposition and entanglement alone are enough to account for the power, without invoking metaphysical claims. While multiverse interpretations remain an intriguing philosophical lens, researchers stress that the engineering success of Willow does not equate to proof of parallel worlds. Physicists have also built general frameworks to classify such multiverse ideas. Max Tegmark and others outline levels, an extension of space beyond our horizon, bubbles formed by inflation with different constants, the quantum many worlds, and the broadest level, which treats all consistent mathematical structures as universes. Cosmologists Brian Greene and others use similar terms. These categories help distinguish between variations, but crucially, none of them yet offers an experimentally accessible test that can confirm another universe exists. The taxonomy is helpful for clarity, but proof remains out of reach. That tension encapsulates the status of the multiverse in 2025. On one hand, the math behind inflation and quantum theory naturally allows for many universes. Equations support the logical possibility. On the other, equations alone cannot demonstrate reality. Observational astronomy has so far found nothing unambiguous, whether in the form of cosmic microwave background anomalies or direct signs of bubble collisions. Similarly, quantum processors push technology forward, but have not revealed metaphysical truths. Evidence is absent even though theory points toward possibility. Skeptics emphasize the need for restraint. They warn that treating statistical quirks as signs of another universe is like seeing patterns in random static. Every high-precision dataset produces irregularities, and the challenge is separating real signals from coincidence. Until anomalies pass repeated independent verification, they cannot stand as evidence. Supporters counter that dismissing the multiverse entirely ignores the implications of the very equations that built modern physics. They argue that just because something lies beyond observation today does not mean it never will be testable. Both perspectives matter. Caution ensures that science does not drift into metaphysics without grounding, while openness ensures that speculative but consistent models remain on the table. Historical precedents show the risk of both extremes. Neptune was predicted through math before telescopes confirmed it. Conversely, many anomalies once thought extraordinary, like early claims of cosmic inflation signatures itself, later proved to be errors or misinterpretations. The practical value of multiverse thinking lies not in proof but in influence. Even without confirmation, such frameworks encourage new models of particle physics, fresh approaches to cosmic inflation, and innovative questions about quantum systems. They challenge researchers to consider not only what parameters allow our universe to exist, but why those parameters have the values they do. If other universes could exist with values that forbid life, the fact that we inhabit one where life thrives may be less coincidence and more a reflection of a much larger landscape. Yet the consequences are profound. If multiple universes exist, our sense of uniqueness changes. The distinction between what happened and what might have happened blurs, given that somewhere every possibility is realized. Philosophers argue that this undermines the neat boundary between chance and necessity. But without empirical access, such statements remain speculation, important to consider, but not facts. So where does the idea stand at present? The multiverse remains one of the most provocative possibilities in science, but not one verified by observation. Inflationary theory allows it, quantum mechanics accommodates it, and philosophers explore its consequences. But the line between solid evidence and imaginative mathematics has not been crossed. A confirmed, repeated anomaly in the cosmic microwave background, consistent with bubble collisions, could be the empirical breakthrough. Until then, the multiverse is best seen as a hypothesis supported by elegant math held at arm's length from physical reality. What matters most now is where this curiosity leads us. Even speculative models guide the design of new experiments, from advanced microwave background surveys to refined quantum devices. These efforts generate overwhelming streams of data, each night producing more observations than decades of science once held. This flood of information demands tools capable of finding real signals amid the noise, tools powerful enough to keep pace with discoveries at a cosmic scale. AI, the sky's new cartographer. Astronomy in 2025 is defined not just by telescopes but by algorithms. As new observatories flood researchers with immeasurable quantities of images and measurements, artificial intelligence has become the essential partner in turning raw scans into usable maps of the cosmos. Few facilities demonstrate this shift more clearly than the NSF Vera C. Rubin Observatory. Already producing its first look images this year, Rubin is poised to capture an ongoing record of the sky on a scale humanity has never attempted before. Its legacy survey of space and time, LSST, will scan the sky night after night for a decade, collecting roughly 20 terabytes of data each evening. By the time the survey concludes, the database will contain catalogs on the order of 20 billion galaxies, entries so numerous that no human reviewers could ever process them unaided. The Rubin Observatory's instrument at its heart, the LSST camera, is itself a feat of engineering, nearly the size of a small car, weighing over 6,000 pounds and covering patches of the sky the size of 45 full moons per exposure. Even a single image contains data on millions of objects, stars, galaxies, asteroids, and faint sources billions of light years away. Taken together, the nightly output builds into an unfinished atlas, one that only AI can realistically keep track of. To imagine giving these images to humans alone would be like asking someone to catalog every grain of sand on Earth by hand. In practice, AI models now sort variability in light, detect transient events, flag anomalies, and compress these raw rivers of numbers into data scientists can interrogate by the next morning. The scale has turned AI from a convenient accessory into core infrastructure. The role of AI is not confined to streamlining what humans already know how to catch. Its greatest power sometimes comes from noticing what our eyes miss, rare or contradictory events buried in masses of routine data. Memorable cases often cited out of ongoing survey analyses, an unexpected star cluster that broke the textbook pattern of how such systems mature. Whereas most clusters contain stars of similar age, this group appeared to mix youthful members alongside much older populations. Standard models struggle to account for the anomaly. A human team might never have noticed, since the deviation was subtle and diluted inside terabytes of raw imagery. Yet an algorithm trained to compare distributions across huge numbers of clusters picked out the discrepancy repeatedly until astronomers confirmed it was genuine. Curiosity naturally follows. How exactly do these new systems detect such outliers? A particularly instructive example comes from Oxford University's work on the all-sky automated survey for supernovae Atlas. To help process supernova candidates, they developed the Virtual Research Assistant VRA, an AI tool designed to mimic the evaluation once handled entirely by postdocs. In trials, the VRA reduced the human workload by about 85%, while still capturing more than 99.9% of genuine supernovae, missing fewer than 1 in 1,000 real events. That meant AI could remove most manual vetting without diluting discovery, freeing researchers to concentrate on interpreting results rather than wading through false alarms. Successes like this stand as evidence that carefully trained AI can accelerate science without sacrificing rigor. Still, every gain comes with cautionary lessons. A model trained mostly on images of spiral galaxies risks treating irregular galaxies as errors, discarding what might be extraordinary structures. In this way, bias slips from datasets into algorithms, which then export that bias onto the sky at machine speed. Astronomers are increasingly vocal on this point. AI bias is not an abstract concern, but a systematic hazard. A mistake once confined to cataloging a few stars can now affect billions in seconds. Left unchecked, that could quietly erase the very surprises astronomers hope to find. To counter this, researchers layer AI with checks from citizen science. Volunteers around the world contribute by labeling galaxies or classifying shapes through online platforms. Their collective input generates training sets that improve algorithms, anchoring machine judgments to human perception. When AI begins diverging from those shared judgments, the discrepancy becomes a warning flag. Blending the breadth of machine-scale analysis with the grounding of distributed human classification has proved one of the most effective ways to limit blind spots. In effect, people and machines keep one another honest. The benefits of this partnership are measured not just in efficiency, but in time saved. Historical sky surveys often lagged years between data collection and usable results. By then, many transient phenomena, supernovae, gamma-ray bursts, or near-Earth asteroids, had vanished from view. Today, Rubin's pipeline, strengthened by AI-driven classification, can deliver reliable lists of candidates within days, sometimes within hours. For phenomena that evolve quickly, that speed means astronomers can point other telescopes in time to witness rare episodes of cosmic change. For nearby asteroids, it also provides a public safety function, ensuring potential hazards are flagged before they pass us by. Yet skepticism endures for good reason. Some researchers voice concern that astronomy could narrow its scope if only dependent on algorithmic filters. AI highlights what it has been trained to recognize, but revolutions often come from what appears at first to be noise, signals that do not fit prevailing categories. If future anomalies demand recognition outside an AI's training boundaries, they may never be flagged at all. Critics worry about a gradual drift, where science only progresses in directions machines are good at handling. In this respect, reliance can itself become a blindfold. These concerns underscore why the metaphor of AI as cartographer rather than telescope resonates among astronomers. A telescope shows a raw landscape, but a cartographer determines what to mark and what to omit. AI builds the maps on which astronomers depend, but like every map, the product is interpretive. Some roads are exaggerated, others vanish entirely depending on the method. The maps are indispensable, but only if scientists maintain a healthy suspicion about what may have been left off the page. What preserves enthusiasm despite these risks is the record of unexpected successes. Beyond rogue clusters, AI has flagged galaxies with warped structures, variable stars with irregular cycles, and asteroid trajectories that defy predictions. Each find represents phenomena that could have been buried forever. In each case, the payoff outweighed the risk of bias. The lesson has become clear. If astronomers remain vigilant about systemic errors, AI greatly expands their reach, allowing them to treat the universe less like a static archive and more like a living process in motion. The larger implication is that cosmic research now depends on this machine partnership to progress at all. Mapping billions of galaxies provides a baseline for every other branch of inquiry. Whether it is tracking dark matter distributions, charting dark energy's push on the expansion, or counting planetary systems around different types of stars. Without accurate cartography, these investigations operate blind. That is why astronomers now call AI not a supporting feature, but a cornerstone of modern infrastructure, embedded in celestial research as firmly as the telescopes themselves. Still, for all its transformative role, AI is built to parse what can be observed. The unknowns that lie outside data streams, enigmas that question the very origin of time, demand other methods. As important as cosmic maps are, they still leave one boundary unsolved, the question of beginnings. And it is precisely at that limit where astronomy turns toward bolder experiments, daring to ask what the universe was like before it even had time to exist. Tuesday, before the Big Bang. What does it even mean to talk about a Tuesday before the Big Bang? The phrase itself feels contradictory, because if time started with the Big Bang, then there was no before for any Tuesday or any other day to exist. Yet in 2025, this paradox is exactly where cosmologists are focusing their energy. They are asking whether the universe truly had a singular origin, or whether what we call the Big Bang might have been a transition from some earlier state. To investigate requires venturing into the boundary zone, where our two best theories, general relativity, which describes space-time, and quantum mechanics, which governs matter and energy, collide and demand a still elusive unification. The very earliest instant of the universe forces this clash. In the dense, high-energy environment of the origin, classical gravity falters, and without quantum gravity, a theory not yet completed, we simply cannot describe conditions fully. General relativity works flawlessly for galaxies and stars, quantum mechanics works for atoms and particles but collapse them both into a single point and the math breaks down. Developing even partial ways to describe what happened at that juncture has become the central challenge. Though a full theory remains out of reach, scientists are beginning to approximate. Quantum gravity experiments attempt to simulate conditions similar to those that may have existed at or before the Big Bang. Particle colliders push protons and heavy ions to nearly light speed, probing matter under extreme compression. Researchers then measure whether its behavior diverges from the standard model, looking for subtle traces of new physics. Elsewhere, theorists test models in which time itself is emergent, possibly arising from entanglement at small scales. The effort is not hand-waving. It is a set of concrete scenarios under investigation, each a possible way of showing how spacetime itself could arise from conditions preceding the hot Big Bang. Observatories play an equally important role. Facilities such as the South Pole Telescope and the Simons Observatory are pushing the boundaries of cosmological measurement by analyzing tiny fluctuations in the cosmic microwave background, CMB. These minute variations in radiation encode the earliest structure of the universe, and improvements in sensitivity are now tight enough to test inflationary models and constraint alternatives. By narrowing down parameters like the sound horizon scale, these instruments bring us closer to the limit where speculation about quantum gravity can be confronted with data. The findings so far do not give answers about the before, but they do impose tighter bounds on what early universe scenarios remain viable. One theoretical alternative gathering attention is the Big Bounce model. Instead of a one-off creation, this hypothesis proposes that a previous universe contracted into a crunch reached maximum density and then rebounded into the expansion we now inhabit. This picture allows cosmic history to extend endlessly with universes succeeding one another, but the idea is still highly speculative. Current instruments provide only indirect avenues of testing, such as searching for bubble-like traces in the microwave background or unusual patterns in galaxy clustering. No clear empirical confirmation has emerged, only hints that keep the model on the list of possibilities. Other cyclic universe theories push the recycling concept further, imagining an endless sequence of expansions and contractions in which the universe never had a first moment. They offer the philosophical appeal of avoiding a hard beginning, but again, evidence is missing. What facilities like the South Pole Telescope, the Dark Energy Spectroscopic Instrument, and DAISY surveys can do is reveal whether anomalies exist that classical inflation cannot explain. Any consistent deviation in the CMB or in the clustering of galaxies could signal traces of prior cycles. So far, data tightening has largely reinforced the inflationary picture, though questions at its edges remain unresolved. Accelerator work complements the observational angle. By smashing particles harder and harder, scientists probe the point where space-time may cease to act as smooth and continuous. Some models propose that at quantum scales, space-time is granular, composed of discrete units. If hints of this granularity appear in collider experiments or in cosmic ray anomalies, they could indicate what a pre-Big Bang state might resemble, a phase in which time was not a coordinate but an emergent phenomenon. If true, then asking what came before might be meaningless. Time may crystallize from timeless quantum geometry in the same way that ice emerges out of liquid water. The philosophical consequence is difficult to capture in everyday language. If time itself is emergent, then the idea of a Tuesday before the Big Bang collapses. Rather than thinking of a line of events extending backward, it may be more precise to envision a boundary condition like the North Pole. You can walk north only to that point, beyond which the label ceases to apply. In this analogy, before the Big Bang is not a hidden region but a category error. Some physicists believe that future experiments might make this abstract possibility into a measurable consequence, just as relativity once forced us to accept time dilation as physically real. Skepticism, however, remains essential. The closer we reach toward time zero, the thinner the data and the heavier the speculation. Many scientists caution that discussing a pre-bang may always remain a philosophical rather than empirical pursuit. Observations can press the boundary of earliest expansion, but not necessarily step beyond. Still, the effort is justified, Every increase in precision peels another layer off the timeline, each improvement refining the scenarios left standing. Even if we never see past the beginning, getting closer builds knowledge of how the very young universe behaved. The attraction of bounce or cycle models is easy to understand. They frame the universe not as a singular miracle, but as one act in a longer cosmic story, where expansion and contraction sustain each other eternally. Such a picture may not yet be demonstrable, but it alters how cosmologists think about origins. Instead of creation from nothing, it suggests transformation from something that always was. And if evidence one day favors this, it would reframe cosmology as dramatically as previous turning points in science. For now, the best tools combine multiple approaches, microwave background mapping to hunt for anomalies, particle accelerators to stress, test matter under extreme conditions, and increasingly complex models that knit quantum mechanics and gravity together. Together, they allow scientists to outline the frontier even if they cannot yet cross it. High-precision surveys in 2025 are edging the field toward the threshold where quantum gravity ideas will either be constrained or compelled to evolve. But a proven theory remains elusive, and definitive answers about it before lie firmly in the future. The curiosity gap is plain. If subtle signatures of an earlier phase eventually appear, whether in CMB patterns, sound horizon deviations, or collider anomalies, it would not only rewrite the origin story, but also give researchers an experimental handle on quantum gravity, a pursuit ongoing for generations. That possibility keeps the field alive, knowing that even faint traces could transform the narrative. The irony is that progress toward these enormous questions rarely comes with bold revelations, but through cautious refinements, narrow parameters, and disciplined checks against noise. Observatories report constraints, particle labs flag anomalies, theorists update models. Each step nudges the invisible wall closer. Yet everyone in this field knows what is at stake. If just one of those traces survives scrutiny, cosmology will have expanded into territory once thought unreachable. And that leads to an equally human question: which of these breakthroughs, if they arrive, will count as history-making? Among physicists, that is another layer of speculation, because recognition hangs not on speculation, but on proof. The Nobel-worthy unknowns. What kind of discovery rises high enough to shape the next Nobel Prize in physics? The question lingers in observatories, laboratories, and data centers everywhere, because these awards are not given for promising ideas, but only for results that demonstrate undeniable proof. The Nobel Committee recognizes work that has made the leap from conjecture to established fact. Many of the mysteries at the center of today's research, dark matter, dark energy, inflation, are exactly where proof is hardest to pin down. Yet 2025 feels unusually charged, with several front-running candidates beginning to crystallize into possibilities strong enough to carry Nobel weight. A reminder comes from precedent. Gravitational waves were theorized for a century and finally detected in 2015, with the 2017 Nobel Prize following soon after. What triggered the recognition was not the first signal alone, but the accumulation of multiple detections across upgraded instruments, each one aligning with Einstein's general relativity. Only when the pattern was robust and repeatable did the Nobel Committee act. A similar standard applies today. Any claim about inflationary signals, evolving dark energy, or unexpected forms of black hole mergers will require that same reproducibility across independent teams and instruments before it can be judged prize-worthy. Among the strongest contenders remains gravitational wave astronomy. When the first detection came from twin black holes merging, it was heralded as a triumph of persistence. Now detectors like LIGO and Virgo, supported by CAGRA and upcoming sites, are not just catching single events, but building catalogs. By 2025, they are identifying mergers of unusual character, black holes with masses that seem unlikely, mixed events involving both black holes and neutron stars, and tentative signs that smaller primordial black holes might actually exist. Each new class changes how astrophysicists think about cosmic history, from stellar evolution to the seeds of galaxies. Should one of these rarer signals be repeatedly confirmed with high confidence, it could well set the stage for another Nobel. A prize in this category would mark not only triumph over instrumental challenges, but also the expansion of an entirely new field of observational cosmology. The search for inflationary fingerprints is another strong candidate. Inflation remains the leading explanation for why the universe appears so uniform on large scales, even though it is filled with structure. The theory requires a burst of exponential expansion in the first fraction of a second after the Big Bang, but direct proof has never been secured. The telltale sign would be curl-like patterns in the cosmic microwave background, known as B-mode polarization. These faint patterns would be in direct evidence of primordial gravitational waves stirred up by inflation. Ground-based telescopes in Chile and Antarctica, along with major projects like the South Pole Telescope and the Simons Observatory, are at the forefront of this work. Both facilities are now tightening constraints on possible inflationary models by mapping the background sky with extraordinary precision. The challenge is steep. Galactic dust produces similar swirling imprints that can easily be mistaken for primordial signals. Earlier, announcements claiming discovery of B-modes had to be retracted once dust contamination became clear, a sobering reminder that premature claims can tarnish even world-class efforts. Current experiments have learned from those episodes, layering in new methods to separate foreground dust from true early universe imprints. If a future dataset isolates unambiguous B-modes, it would be considered a definitive breakthrough, and recognition at Nobel level would be almost guaranteed. Dark energy represents a third major path toward recognition. Long assumed to be constant in time and space, dark energy is the mysterious ingredient responsible for the universe's accelerating expansion. By 2025, the Dark Energy Spectroscopic Instrument has analyzed the light from nearly 15 million galaxies and quasars, a record-scale dataset. Its early reports suggest that dark energy may not be perfectly steady, showing mild hints of time evolution. In parallel, the supernova Cosmology Project Union 3 compilation, the most extensive standardized Type Ia supernova dataset ever produced, offers independent signals pointing in the same direction. If dark energy truly evolves, it would mean the universe's fate is less certain than once believed. Instead of a fixed acceleration, the expansion might slow, stall, or even reverse under certain conditions. The possibility alone has startled cosmology because it challenges the assumption that dark energy is just a cosmological constant. The Nobel Committee, however, operates under its own set of demands. These hints from DESI and Union 3 are intriguing but not sufficient. The prize cannot be awarded for a promising hypothesis or for a dataset that only leans toward one conclusion. It has to rest on experimental proof, confirmed and reconfirmed by independent analyses. Caution has been heightened by missteps in the past, from the incorrect claim of faster-than-light neutrinos to retracted inflation signals. As with the false alarms in dark matter detection, the lesson is clear. Only when signals withstand repeated tests across different approaches does the Nobel become possible. At the same time, the prize's history reveals an irony. Many of the most revolutionary theories never won because they remained unproven during their champions' lifetimes. Ideas about multiverses, pre-Big Bang bounces, or quantum gravity structures continue to inspire but remain untouchable by Nobel standards. They shape theoretical debates, but until anchored by confirmatory evidence, they exist outside the prize's reach. The Nobel recognizes what is demonstrably true, not what is most exciting. Some of the frustration among scientists comes from how long that process takes. A community may already suspect the truth of evolving dark energy or inflationary waves, but the Nobel Committee waits for the last shred of doubt to fall away. To some, this feels overly conservative. To others, it's the very reason the award retains its influence, because when it's announced, the world knows the claim has been nailed down beyond question. Thus, Nobel recognition moves slowly, often trailing years behind the first tantalizing headlines. Still, the sense of possibility in 2025 is undeniable. Gravitational wave catalogs are expanding so quickly that unusual sources may soon rise into focus. Inflation experiments are now reaching the sensitivity required to isolate primordial signatures, with observational constraints narrowing each year. Dark energy datasets from DESI and Union 3 are shifting consensus toward time-evolving models. Each of these directions has the potential to transform cosmology, and all are under active experimental pursuit. The more intriguing point is that Nobel recognition often rewards discoveries that open deeper mysteries. Detecting gravitational waves broaden our ability to map the universe, but also raise new puzzles about black hole formation. A confirmed B-mode signal would cement inflation, but leave unanswered what caused it. Evidence that dark energy evolves would undo simpler models and force theorists to rethink the future of cosmic expansion. These are not closures of debates, but accelerants of new ones, and it is this pattern, answers that create even more profound questions, that tends to mark Nobel-level advances. A fitting way to summarize 2025's state of play is straightforward. The next Nobel in cosmology is more likely to follow a clean, repeatable experimental proof than a single sensational headline. Jay-Z's Galaxy Maps, Union 3 supernova standardization, LIGO's expanding catalog, and Simon's Observatory's coming CMB maps are converging on problems central to modern physics. If any one of them produces results so robust that doubt becomes impossible, the Nobel Committee will move. And behind the technical competitions runs a quieter question. Why should triumphs about inflation, dark energy, or gravitational waves matter at all to those outside of physics? For the public, what matters most is how these breakthroughs reshape the way we think about existence itself, even as they remind us of its uncertainty and its limits. That shift in meaning, the human side of discovery, extends beyond data and prizes, touching the oldest questions about purpose and fragility that cosmology was always bound to stir. The existential question. Why wrestle with the end of the universe at all? The question hangs over every discovery because no matter how precise the measurements or how powerful the telescopes, theories still point toward a cosmos that may not last forever. Whether it fades into heat death, folds into a crunch, or rushes toward a rip, the message is the same. Permanence is not guaranteed. This is the existential question, and it matters because it does not erase meaning. It reshapes how we think about it. Fragility does not diminish significance, it heightens it. The three main models of cosmic destiny illustrate this tension. Heat death imagines a universe stretched so thin that no new events occur, only a cold twilight where activity slows to nothing. The Big Crunch imagines the opposite, with expansion reversing and matter collapsing back into an ultimate density. The Big Rip envisions acceleration running away so violently that even atoms are pulled apart. These concepts are stark, but none say that existence is pointless. Instead, they force us to grasp how remarkable it is that we live in the brief era when galaxies shine, stars burn, and life appears. Meaning is not determined by what cosmic chapter closes the book. It emerges because we are alive inside it now. Recognizing limits sharpens experience. If the cosmos has boundaries in time, then every human moment acquires urgency. A sunset or a conversation gains weight because it cannot be repeated endlessly. The absence of permanence magnifies its value. Rather than nihilism, scientific models of endings fuel gratitude for the finite window that is real. Life matters not because eternity guarantees it, but because its scarcity makes it irreplaceable. This insight overturns the idea that science drains away mystery. Learning about galaxies evolving or forces threatening to dissolve matter does not strip the world of wonder. If anything, it intensifies it. Knowledge of potential cosmic collapse becomes a reason to marvel because it illuminates how improbable it is that life has surfaced at all. A violent equation describing expansion does not negate beauty. It casts everyday awareness into sharper relief. That equation reminds us that reality permits thought for only a narrow span, which makes the act of experiencing thought itself astonishing. Knowing that dark energy accelerates the expansion of space connects to a human truth, nothing remains fixed forever. The moral consequence is direct. Live fully now, because constancy is not promise. By the same logic, debates over black holes or multiverses derive their importance not only from possible answers, but from reminding us that meaning happens in the asking. To search, to question, to discover, these acts transform uncertain existence into a chosen purpose. Lessons also invite humility. Stars use up their fuel, galaxies collide, and even the most durable cosmic structures erode with time. If everything breaks down eventually, human continuity cannot be assumed either. Fragility is not a flaw, but a condition of reality. Seeing this clearly does not erase value. It emphasizes responsibility. One span of time exists for each generation, and within it choices matter precisely because they are limited. Once gone, they do not return. This same fragility can be a source of meaning. If the universe were to cool in a heat death, then this era, when stars still burn, would represent a rare chapter when life could happen at all. If collapse awaits, then our moment stands in the interval of openness before contraction. If forces someday rip galaxies apart, then the present is the sanctuary where conditions align to support thought and connection. What each version has in common is that our time is extraordinarily unlikely. That rarity itself creates significance. Rather than leaving us diminished, cosmic endings leave us magnified. Stars, too, have short lives, yet their endings seed the heavy elements that build new structures and eventually living beings. Temporariness becomes generative. Human lives, though brief, can shape knowledge or culture in ways that ripple beyond their span. Mortality, rather than negating meaning, drives us to create it. On the largest scale, transience itself is what pushes significance into existence. Even data-heavy projects reinforce this connection. The Rubin Observatory, already delivering first images, will soon record around 20 terabytes of sky data each night and track thousands of transient events, supernovae, shifting stars, near-Earth objects, on a daily cycle. The cosmos is a cauldron of constant change, and our era happens to be one where we can witness it. Discovering and documenting these fleeting phenomena gives way to our time because the universe will not always offer them. The transience visible in the sky mirrors the transience of human life, and recording these moments is both science and meaning-making at once. This realization, that value is created within constraints, is the core of what cosmology returns to us. Fragility turns into the condition under which urgency becomes real. A universe without limits would render moments interchangeable. A universe with limits forces moments to matter. To exist now, inside a cosmos not guaranteed to continue unchanged, is to bear an extraordinary opportunity. Science, far from reducing awe, nurtures it. By exposing catastrophic endings and cosmic impermanence, it transforms ordinary life into something worthy of reverence. The same data that point toward heat death or acceleration also remind us that for now, galaxies spin, planets orbit, and consciousness has awakened. Witnessing this fragile slice of time is already a gift, and acknowledging the scale of its impermanence makes its presence more vivid. There is one more profound implication. Perhaps intelligence is the way the universe becomes aware of itself. Without observers, stars burn and galaxies move in silence. With observers, events become memories, and equations become the woven story of existence. The universe may not provide meaning on its own. It emerges through the beings who ask questions. For however long mind exists, the cosmos is stitched to awareness, and that connection alone enlarges significance. In the end, uncertainty itself is what deepens purpose. We cannot know if reality ends in heat death, collapse, or rip, but knowing that an end of some kind is possible intensifies the importance of what exists now. Fragility is not weakness. It is exactly what presses us into appreciating life, investing in connection, and building knowledge. That is how meaning arises in a universe that offers no eternal guarantees. And so we arrive at the human question: does the thought of a finite universe reduce your sense of purpose, or does it sharpen it? Share what you feel in the comments below, because the way we answer may say as much about us as it does about the cosmos itself. The stage is now set to bring this story together to see how science does more than describe equations and outcomes. It reveals that our position in the universe is both precarious and extraordinary, and that curiosity itself might be the most vital response to fragility. Science reminds us that our place in the universe is both fragile and extraordinary. Out of billions of galaxies and stars, awareness has emerged here on a planet so small it would vanish on any cosmic scale. That perspective does not diminish us. It reveals how rare this moment is and how much depends on how we use it. Modern tools like JWST, DESI, Rubin, and quantum processors expand what we can ask even as uncertainty remains. Our survival lies not in knowing every answer, but in refusing to stop asking. Curiosity is survival. If you enjoyed this cosmic tour, hit subscribe to keep asking the big questions together.